Hello, everyone. This is Ali Rasek. I'm a senior engineer with HDR in Vancouver, and I'm trying to recapture my presentation last week in the CDA conference in Saskatoon. The title of the paper was Verification of Seismic Analysis of a New RCC Dam in High Seismicity Region. I work with HDR Corporation, which is a Canadian company headquarters in Toronto, and my colleagues Dikshant Saini and Adam Tutman are from our parent company, which is HDR Engineering in the US. The outline of the paper is introduction and then verification process for seismic structural simulations, then verification of Newport Dam seismic simulations, consisting of software verification, finite element analysis model, and FEA simulation results. And then I will proceed to summary and conclusions. Introduction. I skipped this slide. This is city of Newport in Oregon, which is a majestic tourist city, and it has about 11,000 residents. And there is a fishing fleet that they use two-thirds of the fresh water. And there is only one water source, which is this Big Creek River. And right now they have two dams on this river. This is the dam bridge scenarios studied by another company and indicating that this is a high consequence dam bridge. Review of Big Creek Dam number 1, which we may call it BC1, and it's on the lower side of the river, constructed in 1951, and the type is embankment dam, and it has a height of 21 feet and crest width of 12 feet. Big Creek Dam number 2, or BC2, is constructed or was constructed in 1968 and was rated in 1976. Again, type is embankment dam, and the height is 56 feet and crest width is 20 feet. The replacement dam is considered by City of Newport. And why they consider that? It's because the existing dam foundation are high plasticity sealed and it's soft, or they are soft. There are seismic concerns, meaning that it will likely fail for 2,500-year event. And even the more frequent, less severe earthquakes, they will have operational impacts. Alternatives were evaluated. One was modify and raising existing PC2 dam, RCC replacement dam, which so far has been the top contender, and a new embankment dam and desalination. Some of these alternatives are still being considered by the owner, despite we progress to 30% design. And a picture of comparing a gravity dam versus arc dam. That was one of the intentions of our study, to decide between the two. Gravity dam transfers the load, the lateral load, to the base, and arc dam transferred the load partly to the base and partly to the abutments on the two sides. The final decision was something in between. We decided on a curved gravity dam, which basically, I mean, this is a high seismicity region, and we wanted overturning stability caused by thickness of gravity dam and sliding prevention caused by the curved shape, which prevents movements towards the downstream. Again, a picture of the future dam that is going to be built. Our decision in advance was, as I said, curved gravity dam, 140-foot tall RCC dam, crest length of about 400 feet, replacing both dams that I previously mentioned. 1 year RCC strength of 3000 psi, which is on the lower side and mostly dictated by the construction side. And it needs about 50 feet of alluvial excavation to get to competent rock. On the left abutment, we will end up with really competent rock. And on the right abutment, top of competent rock would be pretty much lower, like we don't have a strong abutment, and we need remediation such as abutment on that side. But this is not studied in part of this study. Different curvatures were studied, and the decision was made based on the best curvature that would sit on more competent rock or be very close to competent rock on both sides. And the 500 feet radius was selected. Again, some sketches of the dam per 30% design, which you can find in the paper just for your reference. Now, describing what the verification process for seismic structural simulations have been. The basis of the verification is ASME 2019 publication on verification and validation, which have rigorous definition of verification versus validation. The main question to answer for verification is whether computational model accurately represent the underlying mathematical model and its solution. And the level of accuracy requirements can be influenced by public perception. That's very important, like how much safe the public expects from a dam to be after a seismic event or during a seismic event. Economic considerations, how much money could be spent on analysis or how much money can be spent on construction. Again, relates to public perception, how much the public is willing to spend, and the engineering judgment, which is related to having good engineers with good judgment. Verification process of the simulations obviously could not go further than the project schedule, cost, and scope. And the verification assessments consider numerical analysis and software quality engineering, programming errors in the computer code, and numerical error estimation. However, in this study, we don't do numerical error estimation, and we are not discussing validation, which is like basically comparing the simulation results with test. What were the verification steps that we really performed? We performed rigorous software value verification for LS-DYNA to be used for earthquake analysis of dams, testing whether the results or the typical results make sense. And this word verification versus validation is not exact. I know that the software engineers sometimes call this process software validation. So, I mean, I'm not carried away by naming, so I call this verification per ASME, and we stick to that in this presentation. rigorous check and review of the geometric model, review of the different aspects of the FEA model, such as materials, seismic input, very important, very, very important seismic input because it's sometimes given to us structural engineers like as a black box, and I have been in scenarios where they have been troublesome, like we have received the wrong seismic input, which has caused miscalculation and miscommunication and misconclusion. That's very important. Mesh size, element size, boundary conditions, they are all reviewed. Mesh and time step convergence is a big part of our verification. And we also do check the dead load, lateral load, and hydrostatic load and their results. For seismic response, we increase the order of complexity and accuracy, which we sometimes call progression analysis. And we start with equivalent single degree of freedom, proceed to 2D models, and then we end up with detailed nonlinear 3D models. And we also perform energy checks. Now, what was the process for verification of Newport Dam seismic simulations? These are big picture view of the dam and foundation model in the left, and a close-up of dam monoliths created in for LS-DYNA simulations, which is shown in the right. Like the close-up is shown in the right. Typical material properties. Materials remain mostly elastic, and the source of nonlinearity is the interfaces, as is the state of practice is in concrete dam engineering, is that we study basically failure planes and nonlinearity of the interfaces. So I have shown the typical material properties and emphasizing 30% design, as this property assessment will improve for next phase. Typical static analysis, including weight and hydrostatic and uplift load, and this could easily be verified by comparison to the hand calculations. Now going to seismic hazard, I have shown a little bit more information from the basically seismic hazard report we received from another company. And this picture shows 2500-year hazard aggregation for 16.16 second period. And I have shown the other characteristics. And the whole point of this is that, as is shown in the bottom left, the Cascadian subduction zone interface is the most important with 90% contribution. And the rupture is at about 24 kilometers, which is very, very close. That's why it's dominant. Typical seismic hazard, and the response spectrum for MCE is shown in between. MCE is the 80 percentile subduction zone for interface, and Cascadia subduction zone. And the acceleration or pseudo-spectral acceleration ranges from 0.9 G, which is PGA, to 2.5 G response, which is actually at about close to primary period of the system. The CMS method was used for basically scaling the records that were given to us. This is a typical record in horizontal direction, again from the report, giving us the acceleration, velocity, and displacement, and the correlated spectral values for this. Also the area's intensity. And what I keep on saying is that although we may not, I mean, maybe it's not even necessary that we totally understand the complex uh, calculations that those hazard guys go through, but we can always perform sanity checks. We can compare the acceleration spectra with what USGS give us. We can create the easy acceleration response spectra for the record and compare with the design spectra. And I cannot tell you, I can tell you that almost every single time I find that I should ask for modifications. And the one time that I didn't ask, I was in trouble. So, I mean, this is the most important sanity check that we should perform as structural engineers who is using those records. The primary mode of vibration of the dam, as I said, is about 0.16. And this is a comparison of the sliding between a straight dam and curved dam, which obviously shows that the curved dam is basically geometrically restrained and cannot really move a lot. So it's a better option for design. That's one of the reasons that we decided about this option. Energy checks we always perform as part of our sanity check and verification. And it's critical for verifying the accuracy and the stability of seismic analysis. We track damping, hourglass energy, internal energy, kinetic energy, total energy, and sliding energy. And they should add up. And as is seen in this picture, most energy loss was through sliding and frictional energy loss. 2D verification was also performed, basically creating a slice of the model. And dam, rock foundation, a hysteresis model of silt, and compressible model of reservoir was created. Outcomes will be used in verification of the 3D analysis results, meaning whether they are on the same ballpark, and also this is part of the progression analysis, as I mentioned. Also, the results will inform changes to the more sophisticated 3D model, such as whether it's really necessary to use explicit reservoir model or added mass, equivalent added mass is adequate. Or the same thing for silt, whether it's adequate to use added mass representing silt, or a explicit model of the silt will change the results. Now, going to summary and conclusion. Extensive FEA static and seismic simulations were performed for 30% design of a replacement RCC curved gravity dam in Newport, Oregon. The project has been subject of rigorous quality control, namely the formal assignment of extensive analysis checks and reviews as the project tasks. Software verification has been part of the quality management. However, as I said, quality management code calls it validation, software validation. 2D and 3D FEA models, rigorous review of the FEA model imports, sanity checks, and mesh and time step convergence studies were used to ensure the accuracy of the solutions. Also, a structural model seismic response was checked in ascending order of complexity and accuracy. But this is only 30% design, and further seismic assessments and verifications are anticipated for 30%, for 60% design of the dam. And it's all done. Thanks a lot for your attention.